Isaac, you done yet?
Just a few more, Governor. I've almost got it.
There are rules in hockey, right? Like, each period is 20 minutes long, and you can't pick up the puck. Put it in your pocket. There's rules in physics, too. They're called laws. Now, unlike the rules in hockey, which we just made up to make it a game, the laws of physics are things we discover about the way the universe works. So, you can break the rules in a hockey game. Oh my gosh! What is that? He shoots, he scores! He shoots, he scores! He shoots, he scores! He shoots, he scores! The crowd goes crazy! So, you can break the rules in hockey and go to the penalty box, but you cannot break the laws of physics. If I drop this hockey puck, it falls. Every time. That's the law of gravitation, and I couldn't break it even if I tried. Every time I drop it, it falls. I can't drop it and get it to float there or go up towards the ceiling. The laws of physics define the way the universe around us works. Now, these aren't things that we make up. The laws of physics are the way things are.
Gravity. It's not just a law. It's a good idea.
Some of the most basic and fundamental laws of physics were formulated by this guy, Sir Isaac Newton. Newton's 3 laws define basic physics. Everything else starts from there. So, if you want to score with physics, you have to get past Newton. Mike Richter here. 10's goal for the New York Rangers. Hey, Mike.
How you doing?
All right, thank you very much. So you ready to get into some Newtonian physics?
Absolutely.
All right, that's good to hear. You're just standing there, right?
Yeah.
That's Newton's first law.
That's it?
That is it.
Wow.
An object at rest tends to remain at rest.
A body in motion tends to stay in motion. Just standing here, we are proving Newton's first law.
Right. If nothing pushes me, I won't move.
Right, and if you're moving, you'll continue moving until something stops you.
Wait a minute. If I just glide on the ice, I stop.
Yes, but something stops you, Mike, a force. And no, it's not the dark side. In this case, the force is the friction between the ice and your skate blade. According to Newton, if you hit a puck into outer space...
Michael, please.
Woo! Wow, nice shot. With no air, gravity, or friction to slow it down, it would keep going forever. The velocity of a body remains constant unless acted upon by some outside, unbalanced force. Like the boards. Unbalanced forces change your velocity and they change the direction in which you're going. Like the wall. Stop me. Ow. When we tap a hockey puck back and forth down the ice, we're applying unbalanced forces to it, changing its velocity back and forth. When 2 hockey players collide, their velocity changes. So, Dave, what can you tell me about inertia?
Well, you mean like not wanting to get out of bed in the morning?
Well, sort of. Right now we have inertia. It's to keep us moving until something comes along to stop us. Whoa! And now we have inertia as well. Our inertia is to keep us stopped until some outside force comes along and moves us. You got it?
Yeah, I got it.
You sure?
Yeah.
All right, he's got it.
Ah, so that's why Newton's first law is sometimes called the law of inertia.
Exactly. So that's it. You're doing Newtonian physics. Are you ready for the second law?
Yeah, I'm ready. I'm really ready.
When an unbalanced force acts on an object, it creates an acceleration in the direction of the force. Whoa! Yes! Whoa! And the acceleration is directly proportional to the force and inversely proportional to the mass.
Say what?
So, force, mass, and acceleration are all interconnected. They all affect each other. Newton's second law looks a little bit like this. Force equals mass times acceleration. Okay, so if I took a shot on goal and I only gave it this much force,
Because you only applied a little force, you only got a little acceleration.
exactly, I'd never score that way. Now, if I applied a lot more force, well, I might not score that way either, but I got a lot more acceleration. Now, what if the puck had a greater mass? What if I hit it with the same force?
You get less acceleration.
Exactly, Joe. Now, let's say the puck had less mass. I'd get a lot more acceleration with the same force. You see, it's all proportional. Force equals mass times acceleration. So, we can plug in numbers to figure out how much force on a certain mass will give us a certain acceleration.
Okay, so you'd measure mass like you would weight.
Right?
Acceleration is how fast an object moves from one speed to another.
Exactly.
But how do you measure force?
In newtons.
Oh, that guy again.
Right, because in Newton's second law, he defines a unit of force, Newton, so they named it after him.
Uh-huh. What the heck's a Newton?
Well, there's Newton the cookie and there's Newton the guy. What we're talking about is this kind of Newton. But see, it took newtons to throw that Newton. A Newton is a unit used to measure force, just like we use feet or meters or any other derived unit to measure something. Now, in an equation, it looks like this. Now, that n there, that stands for Newton. So, how much is a Newton? Well, let's say this box here weighed 1 kilogram. So, 1 Newton would be the force required to accelerate that box 1 meter per second squared. Assuming there's no friction, the force it takes to get 1 kilogram accelerating at 1 meter per second squared is 1 Newton. Let's say I weighed 68 kilograms. Now, the force required to give me an acceleration of 1 meter per second squared would be 68 newtons. Oh. Right! So, that's Newton's second law.
Okay, I'm with you. When a guy out on the ice checks another guy, the force he hits him with is a function of his speed and his weight.
Exactamundo, Mike. Are you sure that aside from being a superstar goaltender, you're not also an expert in Newtonian physics?
No.
You're sure?
Yeah.
For every action, there is an equal and opposite reaction.
I guess we're ready to move on to Newton's third law. You ready?
Yeah, I'm ready.
Standing here, I am proving Newton's third law. My skates are pushing down on the ice, and the ice is pushing back up against my skates. The forces are equal and opposite. If they weren't, I'd either fall through the ice or go up towards the ceiling. We can show what Newton's third law looks like by having Joe here push off of Brian. Okay, Joe? All right. Let's take a look at that on instant replay. Joe is exerting a force in this direction. That's our action. The equal and opposite reaction causes Joe to move away from the direction of his force. And look what happens to Brian. Equal and opposite, right? But let's say I did this. My right hand is pushing against my left hand, so my left hand is pushing back against my right hand with an equal and opposite force, but nothing moves. Because the forces are equal and opposite, they cancel each other out and create an equilibrium. But if I pushed against the boards, there's still an equal and opposite reaction, but it doesn't balance out and I move. That's because the forces are acting on two different objects, the wall and me. The forces are unbalanced. Newton's third law explains why we can skate. Now, when I push against the ice, it pushes back against me. And I move.
Well, wouldn't the ice have to move too?
Well, it does, but it moves such an infinitesimal amount that you can't see it. It's sort of like when you jump, okay? Like this. Because you're exerting unbalanced force on the Earth, it has to be accelerated away from you and gain a momentum equal to yours. Try it. So, that's it. Those are Newton's three laws.
Reaction.
He's not much of a skater, is he?
No, math is more his thing. So, I'd like to thank Mike Richter of the New York Rangers, Brian, Joe, and Dave, and of course, Sir Isaac Newton.
Physics rocks! Aye!
For helping us out today on Sports Figures with Newton's hat trick.